All right, so today we're going to start our first section, functions and graph, section 1.1. And first thing we're going to talk about is just different types of numbers, okay, different sets of numbers. This diagram basically summarizes all the different kinds of numbers that we can have, starting from the simplest numbers with counting numbers, going out to whole, integer, rational and irrational, and then finally the reals. Okay, kind of informally, can anybody just tell me what the counting numbers are? What are counting numbers? What do they start with? Maybe what they don't include? Thoughts on that? Counting numbers. What number do you start with when you count? Yep, Augustine?
1.
1. So counting numbers start at 1. They don't go lower than 1. So when you count, you don't count 0, 1, 2, 3. You start at 1. They go up to infinity. But is there anything counting numbers don't include?
Negatives.
Yep, so we got that by saying they start at 1 and go up. So they don't include negatives, but they also don't include, James? Yeah, decimals. Okay, no decimals. Well, there's certain problems if we only are going to allow ourselves to use counting numbers. Certain calculations you would never be able to do. Addition would work fine with counting numbers. Anytime you add a counting number to another counting number, the answer is a counting number. Subtraction, we could run into problems. Multiplication, I think multiplication would be okay, but division wouldn't always be okay. And we'll get to that. Like if you divide a counting number by another counting number, the answer might not be a counting number. It depends. Let's look at an example with subtraction. 3 minus 3. Okay, we said counting numbers start at 1 and go up. So if counting numbers are the only kind of numbers you're going to use, this is undefined. You cannot do that. Okay? You can't do that because the answer that we really know this is a number. It's not a counting number. 0. Okay? So that gives us our next set of numbers. Okay? Whole numbers. Okay, whole numbers include 0. That's the only difference between whole numbers and counting numbers. They start at 0. They go up to infinity. No fractions, no decimals. Can anybody think of a problem we could still have, though? Either doing addition, subtraction, multiplication, or division. I'm thinking specifically subtraction, where if you take a whole number, another whole number, and you subtract them, something happens that we can't deal with just whole numbers. We need this next set. Yeah. Yeah, can you give me an example of how that could happen? Like a whole number minus a whole number comes out negative?
3 minus 5.
Sure. 3 minus 5. Okay. If the only kinds of numbers you understand are whole numbers, this is undefined. That's impossible. You can't take away more than you have, practically. You know? So that's our next set of numbers. Those are integers. Integers give us our negatives. Okay, so now when you have integers, you have positives and negatives. Still no fractions or decimals. But even with integers, and even just sticking with basic add, subtract, multiply, divide, we can still have a problem. Anybody think of a calculation you could do with an integer and another integer, but the answer is not an integer? Something you could do with 2 integers. You can try adding, subtract, multiply, or divide. Yeah, Augustine.
Dividing 2 negatives. Oh wait, no.
It depends. It depends what they are. So dividing, can you give me an example where you divide 2 numbers and you don't get an integer for the answer? There's no one right answer. There's a ton.
3 divided by 2?
Sure, 3 divided by 2. 3 is an integer. 2 is an integer. Okay? You're dividing 2 integers. But the answer is not an integer. Okay? We have to go outside the set of integers to find the answer. Okay? And that's where we get rationals from. Okay? So now we have fractions. Okay? Practically 3 divided by 2, if you're dealing with physical objects, that doesn't make sense. I can't take 3 objects and divide them equally between 2 people. That's impossible, right? So in fact, the example I have here pretty much is our definition of a rational number. It's a fraction of the form a over b, where a and b are both integers. Top and bottom are integers. There's only one value that b cannot equal. What's the only value that you cannot have for b? Because if you had that, it would be undefined. Oh, Alex?
Pi.
Pi is, well, if you put pi in the fraction, then it wouldn't be rational. It would become irrational. So a and b, I'm thinking of a number that is an integer, but it cannot go in the bottom of the fraction. I think it is an integer, but it can't go in the bottom. Jillian? 0. 0 is an integer, but you're not allowed to put that in the bottom of a fraction. A and b, any integer you want, except b can't be 0. And for most practical purposes in everyday life, I think rational numbers are sufficient. Whether you're cooking and you need 2/3 of a cup of something, that's good. When you start to get beyond your rational numbers, now we're getting more theoretical. Okay? Your irrational numbers, these are numbers that cannot be written as fractions. Rational numbers can be, irrational numbers cannot be. Anybody give me an example of something that's irrational? We already heard one today. What did you say, Alex?
Pi.
Now, pi is irrational. We can't prove that. We think it's irrational. We've never seen a pattern. But there's other kinds of numbers that also come out irrational. Anybody know what those are? Yep.
I.
What is it? I?
Or is that imaginary?
Yeah, that we're getting a whole other thing. But that's I'll talk about imaginary in a second. So I'm still thinking of a number that is real, but it's irrational. Cannot be written as a fraction. These kind of numbers come up a lot when you do the Pythagorean theorem or the distance formula. Anybody remember what you have to do in the distance formula that causes you to get decimals quite a bit? Yep.
Squared.
Not squared. Close. You're very close. But. Brianna? Yes, square roots. Square roots of numbers that don't come out nice. Okay, non-perfect squares. Square root of 2 is irrational, and I could prove that to you. I could prove that from now till the end of time. There will never be a way to write that rationally. I can't quite do that with pi, but we kind of assume it's irrational. And together you take all your rationals and irrationals, and that gives you your real numbers. Okay? The way I've drawn this, you can think of each number set as inside the other. So if something is a counting number, it's automatically inside the whole number box as well. If you give me a whole number, it's automatically in the integer box, which is automatically in the rational box, which automatically falls under the reals. One way, if it's confusing, is to think of it as places. Think of this as like Boston, counting numbers, Boston. Whole numbers, Massachusetts. Integers, the United States. Rational numbers, North America. If you're in Boston, you're automatically in Massachusetts. But does it work the other way around? If you're in Massachusetts, are you automatically in Boston? No, it doesn't work the other way. Okay? So if you're an integer, you're automatically everything outside of that box as well. But if you're an integer, you're not necessarily a whole number. It doesn't work the other way. Somebody brought up the idea of I. We're not going to talk about that at the beginning, but we will eventually. I is an imaginary number. And together, if you take imaginary numbers and real numbers, you get complex numbers. Okay, but for now, we're going to stick with reals. Okay, some of these number sets, like rationals, integers, and reals, have abbreviations we can use. Okay, and those are what the symbols look like if we want to abbreviate those number sets. So integers kind of looks like a Z with a double line in it. for the diagonal. Rational numbers are a Q. If you think of when you divide two numbers, you get a quotient. So the Q kind of has something to do with rational. And for real, they use an R that looks like that. So one way we could use these symbols would be to write something like, let's say I wanted to say 4 is an integer. Okay? This is a short way to write it. Okay? What I just wrote there, that says 4 is an integer. This symbol means element of. So what I really just wrote is 4 is an element of the integers. 4 is an integer. Without having to write that whole sentence out. So you might see these letters used as abbreviations. And this symbol, I don't know if that's in your book, probably not in this section, but it kind of looks like an E, except the side is curved instead of like a capital E. It's not straight. Any questions on those symbols? The Z for integers, I'm not sure why they use a Z. I think I looked it up once and I saw something about the German word for integer beginning with a Z, but I don't know if that's true. Okay. In math, there are 4 binary operations. If an operation is binary, what that means is it needs 2 things to work. For example, if you want to add, you can't add with one number. Addition is an operation where you need a first number and a second number. An operation in math that's not binary is square root. If I give you a number and ask you to take the square root of it, you only need one number. You don't need 2 numbers to take a square root. All of these need 2. So we're going to look at some properties involving addition. I'm going to use the variables a, b, and c. And a, b, and c can be any real number. It can be a positive, can be a negative, fraction, decimal, 0, a, b, and c, any real number you want. Okay. And the first one, I already kind of touched on this earlier, is closure. Closure is the idea that if you take, for example, a number that's an integer and another number that's an integer, and you do an operation on it, the answer is an integer. If that's true, then we say our set is closed. Okay? So in our example here, I'm using addition. If I take a real number and I add a real number, the answer will always be a real number. Let's say I did subtraction and I used whole numbers. We saw that that is not closed. An example is 3 minus 5. That's a whole number minus a whole number. The answer is not a whole number. So because that happens, we would say subtraction using whole numbers is not closed. Right? Another example with division. 5 divided by 3. 5 is an integer, 3 is an integer, 5 divided by 3 is not an integer. So we could say division with integers is not closed, meaning you might divide 2 integers and not get an integer answer. Can anybody think of an operation that's pretty much always closed, no matter what number set you use? So one of these 4 operations, you can use any number set you want, from counting numbers to real numbers, and it's always going to be closed. Well, let's think some of the operations we know that are not closed. I just gave you examples. What's one operation that might not be closed, depending on the number set that you're using? Yeah? Subtraction might not be. Now, if you're going to use integers, subtraction is going to work fine. But if you're going to use counting numbers or whole numbers, subtraction might not be closed. Okay? So it's not subtraction. What's another operation that's not closed, or might not be, depending on the number set you use?
Division.
Division, absolutely. I just said earlier, if you divide two numbers that are whole numbers, you might not get a whole number. So division's not always closed. If you pick rational numbers or higher, it is. Okay, okay, so we've eliminated 2. Any guess which the operation is always going to work? No matter what number set you pick. Is it addition or multiplication? Or both? Could be both. Well, Cody? Yeah, I think both of them are going to work. Even if you go to the most specific numbers that we can think of, counting numbers. If you add two counting numbers together, you always get a counting number for an answer. Okay? Always. If you multiply two counting numbers together, you're always going to get a counting number for an answer. There's no chance that you multiply two counting numbers and get a negative. That can't happen. So addition and multiplication are always closed for any number set. But you've got to be careful with subtraction and division. Okay, commutative property, I'm going to go through these really quick. Means you can switch the order you're adding two numbers and it stays the same. Associative has to do with how you group them. The order is the same on each side, but we're changing where we put the parentheses. Doesn't affect the answer. Okay, the identity property. Does anybody know what that means? The identity property. It's when you do something to a number with addition and something happens. Or doesn't happen. Yeah?
It stays the same.
It stays the same. Yes, very good. So what's the identity property for addition? What's the only thing you can do to a number and it stays the same with addition? Don't get it confused with multiplication. That's different. You can add 0. Okay, when you start to talk about it for multiplication, what would be the identity property for multiplication? It's not multiplied by 0. That's not good. Yeah?
Multiply by 1.
That's multiplied by 1. Okay. Next one we'll look at is the inverse. The inverse property basically says, is there something you can do to your number to get 0? As long as you're going to work with integers or higher, yes. So if I asked you a question on the test like, for counting numbers, does the inverse property exist? What would you say? For counting numbers, does the inverse property exist? No, it doesn't. For counting numbers, there's no such things as opposites. So you'd never be able to add two counting numbers and get 0. That's impossible. And the distributive property is right there. Okay. A times, in parentheses, B plus C is the same as AB plus AC. Now, I'm not going to write them all out, but you can look over all these properties for multiplication as well. Okay, they're all on page 2 in your book. So you need to know all the properties I just listed for addition and all the properties that are the same for multiplication. Okay, some of them are very similar. Identity is a little different with multiplication. Okay, so look that up. Inverse is a little different. Commutative, associative. And distributive, we really don't have a distributive property for multiplication. You would never distribute if it was B times C in parentheses. You only distribute with addition or subtraction. Okay, so next thing is an equation. Okay, an equation is basically you take two expressions, you put an equal sign between them. Okay, I put 3 different equations up on the board. 2x equals 12. 3 plus 4 equals 2 plus 5. And 5 equals 2. These are all equations. All 3 of them. But I have one of each type. There's 3 different types. Anybody have any comment about any of those 3? Anything at all? Andy, what do you think? Any comment about any of those three equations in general?
5 equals 2.
Sure, let's look at 5 equals 2. What do you notice about 5 equals 2?
5 doesn't equal 2.
It doesn't. That's a contradiction. It's an equation and it's false. It's a contradiction. Sometimes you get that when you're solving simple equations. You have variables on each side, like 3x. This could come up if you had 3x plus 5 equals 3x plus 2. Subtract 3x from each side, the variable cancels. You have 5 equals 2. There's no solution to that equation. Okay, how about, let's look at the one on the bottom. 3 plus 4 equals 2 plus 5. Anybody notice anything about that one? Yeah, James?
Well, it's true.
It's true. Does anybody remember the name of an equation that's always true? Equation that's always true. It's an identity. It's an identity, an equation that's always true. We're going to talk about algebraic identities this year, like when you're solving an equation. If this happens, then that means there's an infinite number of solutions to your equation. And we're going to talk later on about trigonometric identities, involving sine, cosine, and tangent. Okay, this type of equation is called an identity. And how about the one above it? 2x equals 12. Is that equation always true, always false? What do you think about 2x equals 12?
Sometimes x equals 6 is true if it's 7.
Sure. Exactly right. It can be true. It depends what you pick for x. We call it a conditional equation. There's a condition on the equation being true. Sometimes you could have an equation where there's more than one condition that makes it true. For example, x squared equals 4. There's a couple different answers that would make that work. In this case, there is only one answer that makes that equation true. Let's take a look at 3 properties involving equations. Okay, these 3 properties can come up in a lot of different ways. Okay, you see them quite a bit in geometry: reflexive, symmetric, and transitive. We're going to talk about these 3 properties relating to equations. Does anybody remember what the reflexive property means? Again, it can be applied to congruent triangles, it can be applied to parallel lines, it can be applied to equations, but there's a general idea of what reflexive means. Remember what that is. No? So the reflexive property is when something equals itself. Okay, that's reflexive, like A equals A. You see this a lot when you're proving 2 triangles congruent and they share a side. That's when you see reflexive come up. Okay, how about symmetric? Anybody remember what it means if you have the symmetric property? Okay, well, the symmetric property, it's kind of like commutative property. You can switch things, but it's switching what's on each side of an equation. So it's like if A equals B, then B equals A. Okay, so that's symmetric. And how about transitive? A lot of times people seem to remember that one a little bit better. Transitive property. Yeah, Andy?
A equals B and B equals C and A equals C.
Right. Two things equal to the same thing are equal to each other. A is the same as B. C is the same as B. So then A and C must also be the same. And that idea, again, it can be applied to many different things. This is with equations. Okay, so symmetric, reflexive, symmetric, transitive. So what I want to do is take a look at this equation and start to solve it and write down some of the steps that we would use and the properties. So whether we need the commutative property, associative property, reflexive property, symmetric, whatever properties we need to solve this, I just want to see if we can remember them from the last couple pages. Right, so it says 2 times x plus 3 in parentheses equals 6 plus 2x. What would be your first step if you were going to solve that equation? How about John? What would be the first property you need to use?
Multiply the distributive property.
Yeah, distributive property. And as he was saying, that means you're going to multiply the 2 out to the x plus 3. So you have 2 times x plus 2 times 3. Now the next step, you might even do this step with the distributive property. Please simplify what you have there. So 2 times x, 2x. 2 times 3, 6. Now I don't quite have the same thing on the left and on the right, but there's a property I can use to make the left and the right look identical. So what would be the last property to use here? 2x plus 6 equals 6 plus 2x. Yep. Yep. And use the commutative property. It doesn't matter on which side. Okay. And specifically, is this a commutative property of addition or of multiplication? Go ahead, Priya. Which one? Addition. Yeah, this is addition. Okay. So I should add that in. Commutative property of addition, not multiplication. So now we have 6 plus 2x equals 6 plus 2x. What type of equation is that? I mentioned that earlier. Augustine? That's an identity. It's an identity because you can solve, when you solve it, it's true for every value of x. It's impossible to make this equation false. So since you have an identity, there were no other steps to solve this problem. If you were writing what the solution is, you would write all real numbers. That's the solution, all real numbers. Okay. So we're going to take a look at coordinate system. We'll start out one dimension, talk about inequalities, how you graph them, and then we'll get into 2 dimensions and see how that works. Okay, so when we have a one-dimensional coordinate system, we draw a number line, 0 in the middle, that's our origin. Positive numbers right, negative numbers left. Okay, when we use a number line, that allows us to kind of give an order to numbers. Okay? Gives us a way to compare numbers to each other. And there are 4 different symbols that we use when you're comparing one number to another number. Okay, our inequality symbols. Can anybody name one of the 4 inequality symbols that we have? How about Jillian? Yeah, one of the 4. Yep, greater than. So that's one. Danielle, can you give me another one? Greater than? Less than. You got less than? Yep. Victoria? It's 2 more. Greater than, less than. Equal to is an equality symbol, just like an equal sign. So you can't just have an equal sign for inequality, but close. What else can you have? And combining what you said with another symbol. Yeah, less than or equal to. And then our last one is greater than or equal to. Okay, not equal to is also, it's an inequality, but it doesn't really tell me anything. A is not equal to B. Okay, so I still don't know if A is smaller than B or if it's bigger. I don't know. But these 4 symbols give me some kind of relationship between the 2. Okay. If a number is greater, that means it's to the right on a number line. If it's smaller, it's to the left. Okay, so those are 4 inequality symbols. Okay, when we graph an inequality on a number line, okay, we generally use an open circle and a closed circle. This isn't the only way to do it, and this is not the way our book does it. So I'm going to have to show you how our book does it. How many people have graphed inequalities this way before? Using open circle, closed circle. Looks like most people do it that way. Yeah. Okay, when you graph an inequality, the open circle is used anytime you have a less than or greater than. The closed circle is when you have a greater than or equal to or less than or equal to. Okay, so I'm assuming at this point, you guys are all in pre-calc, you know all the steps to do this. Okay. If I ask you to graph something like x is greater than or equal to 2, you can have your number line, number it. You got to choose what kind of circle you need. You got to put it on the appropriate number, and then you need to shade either to the left or to the right. All right, but if you need all those steps, you can take a look in your book. Okay, before we even graph x is greater than or equal to 2, I want to compare these two inequalities. Okay, on the left, I've got x is greater than or equal to 2. On the right, 2 is less than or equal to x. What's the difference between these two inequalities? Like if I were to draw them out and graph them, what would the difference be? Vocal? Nothing. They're the same thing. They're exactly the same thing. I have a preference which one I would like you to use. Anybody have a thought which one I would like you to use? And it's going to tie in with when we draw it in a second. I think I prefer the one on the left or the one on the right. How about Kobe?
The one on the left.
Why?
X first.
What's good about the x being first? There's something good about having the x on the left-hand side.
Because then you know what direction that everything goes.
Right. If you put the variable on the left-hand side, the symbol tells you which way to shade. If you don't do that, the symbol points in the opposite direction to shade. Okay, so generally, I'd like you to write answers like that for inequalities. Okay, so now we just have to decide to graph it closed circle or open circle. Okay, Colby?
Closed circle.
Closed circle. And where do we need to put a closed circle? Where on that number line? Yeah, we're going to put it on the 2. And then which direction do we shade?
To the right.
And then we shade to the right. Okay. So that's how we graph it. Let's try one more. 3 is greater than y. Okay, that's how I started it out. This is the preferred way to write it, but I'm showing you both. Okay, y is less than 3. Okay, Emily, what kind of circle are we going to need this time? Open or closed? So Emily, which kind of circle do you think we need? Open or closed? Yeah, we need open. Open circle, where do we need it? How about Augustine? Where are we going to put the open circle? Yep, open circle on 3. Okay, and John, which way am I going to shade?
To the left.
Yeah, if you do it the preferred way with the variable on the left, inequality tells you which way. Shade to the left. Okay, when you make a number line, you don't have to number everything. What I just did there, numbering 0, 1, 2, 3, something like that is fine. Okay, does anybody know the other way to do this besides closed circles and open circles? Okay, they have a different way of doing it, and it's going to tie in with what we eventually start to learn. And it's with brackets and parentheses. Okay, in place of a closed circle, you can use a bracket. In place of an open circle, you can use a parenthesis. Other than that, the graph looks exactly the same. So, if we were going to graph x is greater than or equal to 2, you put a bracket on 2, Brackets are used in place of a closed circle. And this requires you to be a little bit more intelligent because you have to pick which way the bracket needs to face. The bracket has to face in the direction you're going to shade. Okay, so we're going to shade to the right. And same thing with the parenthesis. Okay, we have to pick the right parenthesis for which way it's going to shade. So I need a parenthesis on 3, specifically opening to the left. And I'm going to shade everything left. Okay, the reason for having a different way of doing it is because sometimes when we solve more complicated equations, we might get an answer like the answer is between, it's greater than 2, but less than or equal to 4. So if I wanted to write that as a, what we call an interval, if I wanted an answer greater than 2, but less than or equal to 4, I could write it just like that. This means the set of numbers that makes my equation true is all numbers greater than 2, and they also have to be less than or equal to 4. All right, so we're going to talk a lot more about this kind of notation, so that's why I'm not really explaining it now. But that's kind of the reason for these symbols. It's going to come up later on. Okay. Sometimes we see a couple inequalities in the same kind of expression here. Does anybody know what this is called? 2 is less than or equal to x, which is less than or equal to 9. Do you remember what that is? Well, when we talk about statements a lot, what are the 2 words that come up a lot when we use inequalities, especially one like this? Two different words. Remember those 2 words? And you have to be very careful which one you use when, because they mean very different things.
And or.
Yeah, and or. Okay, so and or. This is an and statement. This is a conjunction. Right? This is a shorter way to write a conjunction. You could write this out the long way, like that. So what I have down below and what I have here are exactly the same thing. If you're going to split the one up above into 2, you basically look at this part. X is greater than or equal to 2. That gives you the first one. And this part in the blue box, x is less than or equal to 9, gives you the second part. It's important that you can take a conjunction that's together and split it apart, or if I give you something that's split apart, combine it back into one. Okay. If you need some more help with that, you can look at your book and it explains it, but I'm hoping from Algebra 1 you guys can do that. Okay, let's graph it. We can use open circles and closed circles. We don't have to use the bracket and parenthesis here. Okay, what kind of circles am I going to need for this problem, and how many of them am I going to need? Okay, how about Andy? What kind of circles am I going to need? Closed circle. Yep. How many? 2. Okay, Cole, where am I going to put one of my closed circles? On 2. So I should number this. I just decided to go by 2s. So we'll put a closed circle on 2. Brielle, where's my next closed circle? On 9. And now we need to shade. Okay, so Alex, where am I going to shade this time?
In between.
In between. With a conjunction, you generally shade in between. No arrows because they don't keep going. They stop at those 2 endpoints. The only other kind of conjunction you could have would be one that's impossible. For example, if I said x is greater than or equal to 10 and less than or equal to 0. That's impossible. You can't have a number bigger than 10 and smaller than 0. So if I ask you to graph that, you would basically write no solution and leave it blank. Okay. The other kind of graph we can do is a disjunction. That's an OR. So with a disjunction, it's generally the opposite of what you see right here. Instead of shading between the dots, you're usually shading in opposite directions. Okay? So if I change, I'd have to change this a little bit. I could say x is less than or equal to 2, or x is greater than or equal to 9. If I did that, I put two closed circles right where they are, shade in opposite directions. So any questions about graphing conjunctions or disjunctions? I'll leave the disjunction up to you. You can look in your book for that. All right, absolute value. So one way to think about absolute value is geometrically, as the distance from 0 on a number line. Okay, but we can also think about it a little bit more algebraically. Okay, there's really two cases you have to think of for absolute value. If I ask you to take the absolute value of a number, in your head, you look at the number, and you say, is this number greater than or equal to 0? If it is, then I need to do something. If this number is less than 0, then I need to do something different. If I ask you to take the absolute value of a number that's greater than or equal to 0, what do you need to do? If I ask you to take the absolute value of a number that's already greater than or equal to 0, what do you have to do? Oh, Cody?
Can you repeat the question?
So if I ask you to take the absolute value of a number that's greater than or equal to 0, what do you need to do?
Wouldn't that be the answer the same?
Yeah, it stays the same. You don't do anything. So if I give you a number that's already greater than or equal to 0, and I ask you to take the absolute value of it, whatever number I gave you, that is the answer. You don't have to do anything. Okay, but what if I ask you to take the absolute value of a number that's less than 0? What do you need to do to that number? I give you a number less than 0, and I say, tell me the absolute value. What do you need to do to it? Yeah? Make it positive. And if you have a number that's negative and you take the positive of it, what's the relationship between those two numbers? They're, yep. Well, they do have the same absolute value because they'd be symmetrically spaced on a number line. But what's the relationship between a number and if you make it like a negative and then you have the positive version of that number? It's really awkward for me to talk about this without just using the word. Opposites. They're opposites, yeah. Okay, opposites. So if you have a number less than 0 and you need to take its absolute value, the rule is take its opposite. Right, so this is a more formal way of thinking about absolute value. Okay? Kind of takes the concept of distance out of it, and it makes it very mechanical. It makes it so if you wanted to program a computer to do it, the computer would say, okay, he gave me a number greater than 0. I don't need to do anything to it. Oh, the person just typed in a number less than 0. I need to multiply it by -1, which means take its opposite. Okay, so it makes taking absolute value very mechanical, not geometrical, like the first definition.
Why did the negative be inside of parentheses?
The negative, well, A would be, pretend A was -3. So if this was a -3, then the answer would be the opposite of -3, or +3. So A, we're just assuming in this case A is a value less than 0. This is a negative. So then when you plug a negative in right here, the negative and the negative would cancel. And it would become a positive. Here, we're assuming whatever you put in for A is already a positive. So whatever you type here for the question, the answer is the same thing. Does that answer your question? Okay. So I'll look at a couple simple examples. Absolute value of 6. Okay, go ahead, Darren. What would the absolute value of 6 be? Yeah, stays the same. So now, the second one falls into this rule right here. We have a number less than 0. Take the opposite of whatever you see inside the bracket. So what's the opposite of -3? Danielle? 3. Now, you wouldn't want to do that on the top one. You would not want to take the opposite of what's inside, because you already had a number that was greater than 0. So that fell into the top rule. This was the bottom rule. Okay, and the distance between 2 points. All you have to do to find the distance between 2 points on a number line is you subtract them. It doesn't matter the order you subtract them because you're taking absolute value. Okay. Normally absolute value is, normally subtraction is not commutative. Okay, it's not. If you switch the order when you subtract, it makes a difference. But if you're going to take absolute value, it gets rid of the difference. Makes it positive. Okay, so let's say we wanted to find the distance between -2 and -9. We'd have the absolute value of, and Alex, what could I put for a calculation inside the absolute value bars?
2 minus 9. I mean, -2 minus 9.
-2 minus 9? Nope, not quite.
Oh, yeah. Oh, -9. I didn't see anything.
So go ahead, one more time.
-2 minus -9.
Yes, -2 minus -9. A lot of negatives there. So yep, that's going to become -2 plus 9, which is how much? 7. And now the absolute value of 7, we just went over that earlier. 7. So the distance between those two numbers is 7. If you switch it, you're going to have -9 minus -2, which is -7. Then when you take the absolute value, it's still positive 7. Okay, let's look at the 2D coordinate system and summarize that quickly. Okay, in 2D, you have two axes. X is horizontal, Y is vertical. The two axes separate this Cartesian coordinate plane into 4 regions. Anybody know what we call those 4 different regions? Yeah, go ahead, Cody.
Quadrants.
Quadrants. Quadrant 1 is in the upper right, 2, 3, and 4 going counterclockwise. Okay, where the axes intersect, that's the origin. On your x-axis, positive numbers go to the right, negative numbers to the left. On your y-axis, positive numbers up, negative numbers down. Okay, and if I want to specify a location on this grid, does anybody know the name of the thing you need to use? If you want to specify a location in one of the quadrants or on an axis. What's that? How about James? Help him out. What's the name of what you use to say where you want to go on this grid? There's a couple names for it. But it's how you specify a location on here. Casey? Yeah, coordinate. That's one way. Or an ordered pair. Okay, coordinate's kind of a more general term. You can have coordinates in 2D, 3D, 4D. But an ordered pair, you only have a pair in 2D. If you're going to start talking about 3D coordinates, we call it an ordered triple. And the coordinates of our origin, of course, we don't move left and right, we don't move up and down. It is 0, 0. It's called an ordered pair because the order matters. X has to come before Y. Think of it as alphabetical. x, then y. So first your horizontal, then your vertical. Okay, so I want to take a look at the calculator, and we're going to look at how we can zoom in on the xy axis. First thing I want to do is take a look at the calculator, and I want to set it so that I'm seeing a screen of -20 to 20 on the horizontal and -20 to 20 on the vertical. Okay. Any guess which button I need to press to somehow do that? I want my x minimum to be -20, my x maximum to be +20. Same for the y values. Yeah?
Window.
Yeah, we go to Window. Under Window, you can type in, I already have it typed in here. So yours should look just like that when you type it in. X min is -20, X max is +20, Y min -20, Y max +20. They're always written in that order. It's my X's, the second set is my Y's. Let me just hit graph. Okay, so for a problem like that, there's not really anything to show on paper. They just want to make sure you know how to change the window. Any question on how to change the window to the dimensions here? Okay. Is the calculator screen a square? I want to make sure everyone understands this point. Is the calculator screen a square? What shape is it? It's a rectangle. It's wider than it is tall, which means -20 to 20, that's 40 units. Okay? So you're putting 40 units on the width, you're putting 40 units on the height. But if you have a screen that's wider than it is tall, the units are more spaced out horizontally than they are vertically. What that means is images on the screen are going to look distorted. They're going to be stretched. Right? And what I have, actually right here, is a picture of a circle. It doesn't quite connect, but that's just, the calculator's old. Okay? It looks more elliptical. And it looks elliptical because the screen is wider than it is tall. If I want things to look the way they should, proportional, not distorted, you can do zoom square. Zoom 5. And again, pretend it connects, but now that circle does look like a circle. Right, so I want you to keep that in mind. Sometimes things can look distorted on here. Think of it as like a widescreen TV. Sometimes it stretches things out a little bit. Okay, next thing I want to look at is the scale. There was something else besides x min and max. I want to change the scale values to 5. Okay, so you can put your values, I changed mine, but keep them at -20 to 20. And what I want to know is by changing the scale values, what's happening to my viewing rectangle? Okay, the viewing rectangle is that portion of the Cartesian plane you're looking at. Obviously, the plane goes on forever. We're looking at a small window of -20 to 20. Okay, so let's change the scale values to 5. When I do that, what happens to my viewing rectangle by changing the scale values? Any thoughts? What looks different? Yeah?
The spaces get larger and the picture gets smaller.
Yeah. So the picture, let's see if the picture got smaller. I agree, the spaces between the tick marks, they did get a lot bigger. The picture ends up staying the same. So we're not really changing the viewing rectangle when you change the scale. All you're doing is changing how often you see a tick mark. Do you want to see a tick mark every 1 unit? Or do you want to see one every 10 units? Okay. If I, whoops, I messed that up. If I want to see a tick mark every 10 units, I'll probably see 4 of them on the screen right now. Because remember, there's 40 units from -20 to +20. -20. Let's see, I actually might get 5 in there. Let's see. No, we get 4. Okay. You don't see the one on the y-axis. I was thinking you might see one there, but it's the y-axis hides it. Okay. So now I'm getting -20, -10, 0, it's technically there, 10, 20. Okay. We won't be changing the scale very much. Okay. But You can, but it's not something we'll do a lot of. All right, so that's how you deal with the window. Okay, last two formulas we're going to look at are the distance and midpoint formula. Does anybody know what formula the distance formula really comes from? The distance formula is really another formula, just kind of written a little differently. Let me give you a hint. Pretend you had this point we'll call x1, y1. Another point up here which we'll call x2, y2. And I want to find the distance between them. A lot of times when we want to find distances or measure angles, especially in trig, there's a certain shape we're going to draw a lot. Anybody guess what shape I could create? I need to add a couple segments here to do it. Yep. I can make a triangle out of this. And the reason why I'd want to create a triangle is because horizontal and vertical distances are easy to measure on a grid. Diagonals, not so much. But if this point is at x1, this point, well, I know the x value is x2. The distance between x1 and x2, I just need to subtract them. Find out x2, find out x1, subtract. And there's my distance on the bottom. Same thing for the height. This point in the lower right is at a value of y1. This point is at y2, and they're perfectly straight. If I want to know the height, just take y2 minus y1. Now here's the important point. If we know these two sides of the triangle, we can get the third side using what? Formula or theorem. Formula can you use if you know the lengths of two sides of a triangle and it's a right triangle to get the third side? Yep. Okay, what is that? It's the Pythagorean theorem. That's all that the distance formula is. It's the Pythagorean theorem finding the length of this side, x2 minus x1, or x1 minus x2. It doesn't really matter because you're going to square it. Squaring it gets rid of the negative. Okay? And same for the height. You find the height, y2 minus y1, or y1 minus y2. You square it, and you add them up and take the square root. Okay, so that's your distance formula. Okay, and I'll give you an example. I don't think we're going to go through it right now, but this is the kind of question you'd see on a test. Find the distance between the point 1, 4 and 5, 6. I would probably choose to do it this way. Makes the subtraction a little easier to think about. Okay, so you'd fill in those 4 values in those 4 spots, and you could find the distance between the 2 points. Okay, I think if you do it out, it comes out to square root 20, which is 2 square root 5. You do need to know how to reduce square roots, so if you're not sure about that, make sure you look that up in your book. Okay, square root of 20. Try to find 2 numbers that multiply to give you 20, and you want one of them to be a perfect square. Square root of 4 is 2. That's how I did that. Okay, so anytime we can reduce a square root, we will. And the last formula we'll take a look at is the midpoint formula. Okay, the distance formula, when you do it out, the answer is a distance. The midpoint formula, when you do it out, comes out to a point, a coordinate. Okay, and what the midpoint formula says to do is to add the x's up and divide by 2, add the y's up and divide by 2. All right, so the homework tonight will be on page 11, be 1 through 16, 20 to 23, 30 to 32, and 38 and 44.